participants once again in the afternoon session. Now this is the 32th session of day 4 of Wadla 3.0 on topic recent trends in deep learning and applications. So today we have with us Professor Chetan from IIT Delhi. So he is going to talk about introduction to attention and transformer architecture. So before his talk, so I would like to introduce the Professor Chetan sir. So Chetan sir has served as a is serving as a professor in the Department of Computer Science and Engineering at IIT Delhi, holding a joint faculty position at the Yardi School of AI and ANSK School of Information Technology. With an extensive portfolio, he successfully leads various government and industry-funded projects. Additionally, he oversees a thriving computer vision lab and nurturing over 17 graduate students. The lab is occupied with cutting-edge computational resources such as NVIDIA V100, A100, etc., and a substantial RAID data serving spanning approximately 90 TB. His research interests span trustworthy AI, cancer detection, mobility, eco-centric vision, and issues with significant social impact. Okay, so once again, Chetan sir, welcome to the Wadla 3.0 workshop. And now the session is over to you.
Thank you. Let me share my screen. So I hope my screen is visible.
Yes, sir.
Yeah. See, I'm sorry. I think you mentioned visual attention, etc. But yesterday when we discussed, we thought that it would be object detection.
Oh, okay. Sorry for that. Actually, I have read this program meeting, so it was not updated.
I see. Okay. So I'm assuming from the audience that they already know a little bit about the transformers. So what I'm going to assume is that we'll be talking about the object detection from the images. That's why I'm calling it visual object detection. So we'll start with what is the basic problem of object detection, how it has been done through the CNNs. And then in the second half of the talk, I'll also talk about how this object detection can be done using transformers. I would also be happy if we can have the question in between, because one thing that I miss in the online talks is the visual feedback. So when I'm in the lecture, I'm able to see the faces and I know what speed to pick up. But when I'm online, I'm not able to see the faces of the students, so it's very difficult to pick up the right speed. So if you are not understanding anything, please feel free to ask the question in between. I'll be happy to adjust my speed also and my content delivery mechanism also according to the questions. And see, because I'm in a screen sharing mode, I'm not sure whether I'll be able to see the hand raise, etc. So maybe Dr. Rakesh, you can just moderate the session, so you can interrupt me in between and maybe forward the questions from the audience.
Sure, sir, sure.
Okay, and I hope my screen is still visible. I just shifted to the presentation mode.
Yes, sir.
Okay, so we'll be talking about the visual object detection. So let's first talk about what is the visual object detection. So there are various kinds of visual recognition tasks. So something that I'm assuming the audience may be already familiar with is what we call the image classification. So given a particular image, I would like to give a single label to this image. Depending upon the scenario, this label could be various stuff. So for example, I could have asked this question, is it a natural scene or a man-made scene? Is it a forest or is it a beach? Does this image contain a building or not? So the answer to each of this question could be 0, 1. In this case, there are two classes. At times, there could be more than two labels also, in which case we'll call it a multi-class classification problem. But it's a multi-class classification for the image. So given a particular image, get me the label of this image. So it's a global label, it's a global description of an image that we talk about. So this is what we call the image classification. Slightly, let's say more sophisticated than this is what we call the object detection problem. Now, I'm not only asking the label for the image. So just like I said, natural or man-made or uh, uh, the forest or the building. I'm now also asking at which is a location where this label is present. So when I say, does this image contain a building? I, of course, want an answer yes and no. But whenever I say yes, I also want where is that building present. So in this case, typically the where is given by this bounding box. So axis parallel bounding boxes. If I say that this image contains a car, yes, this image contains a car, and I am now like to give 3 bounding boxes because there are 3 cars present in this image. So this is what I will call the object detection problem, in which I give the label, which are the labels which are present in this image, and where is the bounding box. So somewhere in between image classification and object detection is a multi-label image classification, where I could have just said that there is a building in this image, there is a car in this image, there is a person in this image, but I do not say where they are present. So it's somewhere in between an image classification, because typically when we talk about image classification, we're talking about single label. And in this case, an object detection, there can be multiple cars also present. So I have to give a bounding box for each of this car. Now, if I have to solve this problem, how do I do it? So there are 3 techniques which I wish to discuss in this lecture. So the first is a 2-stage detector. So let's try to motivate that. Now, as we have understood, the problem that we wish to do is classification plus localization. So I need to give you a label that there's a cat present in this image, and I have to also localize this cat in the image by giving a bounding box for it. So this is essentially classification plus localization problem. So a naive solution to this could be that, okay, by this time, I'm hoping that you already know what is image classification. You may have already seen some CNN and the transformer and whatnot for the image classification. So what will the typical image classification work like? So I will have an image. I will have some neural network model. So in this case, I'm showing the image of an LX10, but this could be any model. I'm not able to get the pointer. So does anybody know how to get a pointer here? Yeah, okay. All right, okay. So I got it now. So we have an image of a cat. I have my backbone model here. And this backbone model, what I will say is that give me some kind of a feature map. In this case, it's a 4096 dimensional vector. On the basis of this 4096 dimensional vector, I have one more layer which will take me to the 1000 class classification, which is typically an ImageNet classification problem. Once I take this 1000 dimensional vector, it will give me a probability vector, which is of the dimension of 1000 and contains the probabilities of various labels that I wish to classify into. How do I train this model? I train this typically with the softmax loss. Now, this is an image classification pipeline. Now, what can happen is that if I have to solve the object detection problem, as I said, that the object detection problem is nothing but the classification and localization. So I could have as well said that let me have one more branch to this model. So I have this 4096 on the basis of which I was doing the classification. So I can take the same 4096 dimensional vector, put one more layer on the right side of it, or the below vector, and ask it to do a regression problem, which is XYWH. And I predict this bounding box location of this XYWH. And then I can train them together. So this branch gets trained by the L2 loss, which is a regression. This branch gets trained by the softmax loss, which is the classification. And I can train this model for the object detection, right? Now, my question to the audience, the first question, so that you guys don't sleep, is what is the problem with this approach? Do you think that this will scale? My guess is that it will not work, but can you spot why it will not work? Any answers from the audience? Uh, Rakesh, you are able to see the audience, I hope.
Yes, sir.
Any hand raise, anything?
Sir, can you repeat the question, please?
So I described the object detection problem, which is basically a classification and the localization problem. So I need to give a label for the cat, that this image contains a cat, and I also need to localize the cat within this image. Now, I described a particular way in which I could have solved this object detection problem. Namely, I take my favorite neural network architecture, I get the embedding out of this. Over this embedding, I train a classification, and over this embedding, I train a regression for the box. And then I train this backbone or these two layers together with a softmax and an L2 loss. So to me, I proposed that this is a let's say valid way, or this is a right way, or this is one of the ways to solve an object detection problem. But now my question to the audience is, now I'm claiming that although I describe this as a valid problem, a valid solution strategy, this is indeed not a valid solution strategy. But can you spot why this is not going to solve my object detection problem? Okay, so I'll try to answer in that case. Is there any comment? Total class score is more than 1. What do we mean by that? What is total class score? Okay, so let me just see to that. So why it is not a valid problem, why it's not a valid solution strategy is because in this architecture or in this model, what I have implicitly assumed is there is one object in the image. So I'm giving one label and I'm giving one box. Okay. Now, what if I do not have one object? I have two objects, or I have many objects in the scene. So how do I know how many bounding box to output or how many labels to output also? So because let's say it's not a multi-class classification, a multi-label classification as I described earlier. So if there are two cats present, I just cannot say cat. I have to say cat 1 and cat 2 and then its location. So how do I even know how many objects are present in the image so that I can output the right number of boxes? So the way I presented, it's not going to work and I have to do something else for the object detection. Okay. So one way to do that would be that I take a box, okay, and I say that within this box, if there is an object present, and if there is an object present, which is the object type. So for example, one can say here that this box contains a face of a dog. Then I move this object to all the places, and for each location of this box, I try to classify which location has an object present, and then what kind of object that is. Now, if I try to follow this approach, it actually becomes for each location of the box, it becomes an image classification problem, because for each box, now I'm saying that there is only one object present within this box. You just have to classify which object. And because I'm moving this box, we call this a sliding window approach, because I'm sliding this window over the whole image. So I will be able to detect any object which is present anywhere in this image. So I get the localization because this location of the box gives me which location the object is present. And when I classify each box, then it gives me the classification label. So I managed to get the objects. The problem in this approach is that I need to apply the CNN, whatever the model that I'm trying to apply, to a huge number of locations. Okay, so imagine that I have a 2000 by 1000 image, that's the full HD image. So I want 2 million locations of this object, of this rectangle. So which means that for single image, I'm actually converting that to a 2 million image classification problems, 2 million inferences for the classification. So it's going to be very, very computational expensive. Not that this approach have not been tried. I mean, so this HOGs and the half filter that we're talking about for the phase, they were all based upon the sliding window approach. But the key idea there is that the classification for the individual box is a very fast operation. So in that case, the hard features, etc. So that still works because the individual window classification, it's a very fast solution. But if I want to do the same classification through a neural network, then even if, let's say, I assume 1 second for one inference, we are talking about 2 million seconds for one object detection from one image. So it's not a viable solution if I want to do a neural network based object detection using the sliding window. But it gives me an idea how to do that. Now, if the problem is in the number of locations, then it may be an easy problem to solve. So what I can do, I can say that if my object lies over a textureless region, it does not contain an object. Okay, so any object will have some kind of an edges, some kind of an object boundary associated with it. So if there's an object which does not contain any strong boundaries, it's likely not containing any object. Only the places where there is a sufficient amount of strong edge boundary is the viable location for an object, and then I can try to classify only those locations. Now, if I can actually substantially reduce it, let's say 100 boxes which are likely to contain the object, and then classify only those parts, then I'm likely to succeed. So what I'm going to do is, this is something that I will now call object proposals. So I will take an image and I will generate few object proposals. These object proposals are the likely location where the object may be present, and then I will take each of this location and classify it. So I can use my favorite classification engine. I have to just generate the object proposals. Now, when we started the neural network stuff with 2014, there were certain kind of object proposals that one used. Over a period of time, we kept on improving how I'm generating the object proposal. And finally, the solution that we reached is the following. Okay. So as I said, now I'm talking about not the whole image. I'm not going to sample every location in the image and classify. I will be generating some likely regions, some blobby regions which are likely to contain an object, and only on these proposals I'm going to run my inference engine for the classification. Now, in the interest that these days the trend for us is that we do not want any hand-tuned features. So whatever we used to do, whatever feature maps, whatever prediction that we want to do, we want that this all becomes end-to-end in a single network. So what I would like to do is, I know how to do the classification from the neural network, but I would like to say, does the neural network also contains the localization? Can I also generate these proposals from the neural network? So the answer to that also lies within the classification framework. Now, if I look at the feature map of a particular classification model, so I take an image, I try to classify it, whether it's a dog or a cat, and then I backpropagate from my final prediction and say which are the pixels which were responsible for saying this a cat, or which were the pixels which were responsible for saying this is a dog. Then the pixel that will get highlighted are the ones that I actually showed you. Okay, so these are the pixels that we're talking about. So all these pixels are responsible for calling it a dog. So for this image, these are the pixels which are responsible. For this image, these are the pixels that are responsible. And then you can see is that whenever I'm classifying, the right set of regions are actually getting highlighted. So the neural network model that what we have built actually is relying upon a certain subset of the pixels to really say dog versus not dog. And in the context of the object proposal, if I can just say, okay, this is the region where the object is present, and then try to classify that, that can actually potentially solve my problem. So this is how the faster RCNN works. So how it works is that I take an image, okay, and I pass it through a neural network, okay. Now this neural network feature map looks like this horizontal plane that we're talking about. Now, the tensor that we see in the neural network, let's say H by W by C, this is my tensor. So a location within the HW plane tells me which location in my image that I'm really looking at. But if I look at one vector corresponding to a particular location, so remember, if I have HW by C tensor, then at any pixel, I'm taking this C dimensional vector. Okay. So if I look at this C dimensional vector, it tells me what kind of information about this localized location. For this particular location in my image, what is the information that is getting stored in this C dimensional vector? Now, in the case of object detection, if I say that whether there exists an object at this location or not, I should be sampling this location and try to look at this vector. But which kind of object is present, or what is the exact XYWH of that rectangle, is what I can determine using this 256 dimensional vector that we are talking about, for which is across the channels. I'm looking at one particular location in the feature map, but I'm looking at across the channel. So whatever is the number of channel, that will be the dimension of this. So typically in the case of, let's say, many popular classification backbone, this is typically a 256 dimensional vector. So we have HW by D. For example, the HW in many popular cases could be 27 by 27. So we have this ResNet, which is 27 by 27 by 256 tensor that I get at the output for the classification. So I take this 27 by 27, or let's say 32 by 32, just for the ease of description. So I have 32 by 32 HW, and I have 256 as the channel. So it's like 1000 dimension, 32 by 32 maps to 1000. So 1024 dimensional, 1024 locations in my image, and for each location, I have a 256 dimensional vector. So what we try to do it in this case is, we say that, okay, let's take this 256 dimensional vector and ask a question whether there exists an object at this location or not. Okay, so remember, this location maps to somewhere in this location. So what we're asking is, does there exist an object at this location in the image? And I also argue that there exists an object. If there exists an object, I would also like to say which kind of object it is. That's one. And what is its XYWH, the box coordinates. So I ask, object exists or not? If it exists, what are its box coordinates? Okay. So confidence vector, which tells me the objectness, whether the object exists or not, and 4-dimensional vector, which tells which XYWH. So 5-dimensional vector for each location. So if I'm talking about, let's say, 32 by 32 feature map, 32 by 32 by 256, so I'm talking about 1024 location. So what I'm getting 1024 answers, whether the object exists at this location, whether the object exists at this location, and which I can treat as object proposal. So some of these 1024 locations will say, yes, object exists, and this is the location, this is the bounding box. So I will say, okay, this is the bounding box, and I will go for the next stage. As I said, I will try to classify that. So this becomes my overall architecture. So first, yeah. Is there any question? Okay. So the architecture becomes following. So I have my 32 by 32 feature map. For each feature map, I take a 256 dimensional vector across the channel. And for this 256 dimensional channel, I make two predictions. One, the score, which actually tells me object versus not object, and the other, the box coordinate, which tells me which XYWH. And because there are, if it is a 32 by 32 feature map, it's a 1024 location. So I'm potentially getting 1024 proposals out of this feature map. So once I get this proposal, so I have my image, I have my favorite CNN. So this becomes a 32 by 32 by 256 feature map. I take at each location, I take this 256 dimension vector, and I say whether there exists an object or not. If there exists an object, which XYWH. So let us say I find out 3 proposals out of it. So what I do is I say that, okay, take this proposal, look at only this window, the proposal window. We actually crop the feature map from this location. Take the cropped feature map from this location, whatever proposal is, and classify each of this box. Okay. So there are various advantages of this approach. So what are the first advantage? One, I can make this an end-to-end network. So it's all neural network, nothing else. So nothing's going from outside. I can just train it end-to-end. I can make multiple proposals here, okay, in one shot. So I do not take much time. So I just pass it once through the CNN backbone, and I say these many proposals. Now, whichever proposals comes out, let's say 100 proposals comes out. So for these 100 proposals, I take this crop and classify. Typically, this arrow will be only a single layer, two layer, very small neural network here, which means that this arrow is going to be very fast. So even if I have to do it 100 times, it's not 1 second for each proposal. It's typically in millisecond. So overall time, let's say this takes 1 millisecond and I have to do it, let's say 100 times, 100 proposals. So again, maybe let's say 10 milliseconds for it. So overall, I'm talking about 1 second for the whole prediction. So I get my boxes and I am able to classify each of this box. What does it contain? Which label it contains. So this architecture is what we call the faster RCN architecture. This is the name of this architecture. And we call it a two-stage architecture. Why? Because there is a first stage where I'm predicting which boxes. Okay. And then once my boxes have been identified, the proposal has been identified, I crop them from the image and make a get a classification label for each of the box. So it's a two-stage. One, the proposal stage, and the second, the classification stage. Okay. That is why we call this a two-stage architecture. It's a two-stage object detection architecture. Okay. Now, if I have understood what are the two-stage architecture, let's try to understand what are the single-stage architecture would look like. Now, it's not too difficult to imagine because one could have argued even in this case that when I was saying that there exists this object at this location, there exists an object at this location with this XYWH, I could have easily just gone one more step ahead of it and said that also tell me what is the class for this box. Okay, so I would have been outputting in this case the 5-dimensional vector, 1 for confidence and 4 for box coordinates. Now I say that, okay, if I have a 20 class classification problem, so I will be outputting 25-dimensional vector for each of this location. And that will also tell me which box, which class it is. Okay, so it doesn't look like a very difficult step to do, but let's just see how we are going to, I mean, if I actually implement that strategy, how it looks like. So these are my single stage detector. What I'm going to do now. So I will say that, okay, take an image, divide it into a grid. Okay. Now for each of this grid, you predict whether there exists an object here or not. Okay. So you may say that whether there exists an object of this size or not, or whether there exists in this size or not. Now, once you have the two objects, what you're going to see is that, okay, let me just do this for each of the. So what I'm going to do is whichever cell contains object, I'm going to predict the box coordinates. So if I do have an object, I'll say, okay, this object, I will make it thicker. I will increase the confidence of it. If there is no object at this location, I will decrease the confidence for it. I will output 0 confidence, which I'm showing by the thinner lines. Okay. For each location, I say, okay, predict whether there exists an object of this size or whether there exists an object of this size. So this way, I will get many locations now. Okay. So an object of this size exists here, an object of this size exists here, and so on and so forth. Okay. Now, what I'm going to do is, for each of this box, which I just predicted, I'm also going to predict a class probability, which is of which label or which kind of object is present in that box. So let us say this says that there is an object of, I mean, the color now shows the class. Okay. So here there's, I mean, each of the cells says that an object of type dogs exists at this location. All these cells says that an object of type car exists here. Okay, and so on and so forth. So every object says that there is some kind of an object. Every cell says that there is a certain kind of an object which exists at this location. So what I'm going to do is I'm now going to color each box along with it. So each cell had given me that this is the XYWH, and I now colored it according to the class of location. Okay, so I have now box and class prediction according to each cell. And then I'm going to do a final step, which is called the non-maximal suppression. What does the non-maximal suppression do is, imagine like that whenever I will have a object, let us say there is a dog here, that even if I had put a box slightly to the right of it, this box still contains 90% of dog or 80% of dog, which means that it will also say that there is a dog in this box. But the likelihood is that this confidence will be slightly smaller because the correct box contains full object. The other boxes will contain partial objects, so their confidence will be lower. So what we try to do is for each location, we try to find out where is the maxima. So in this case, the maximum is here. And whatever are the overlapping boxes with a slightly lesser confidence than that, then we say, okay, this is the same prediction or this is a prediction for the same object. So I better delete those duplicate prediction. Okay, so whatever is not maximum, I try to suppress it. So that is why this is called a non-maximal suppression. So if I do a non-maximal suppression, I end up in these three objects. But as you can see, there's no explicit proposal stage here. There was a single neural network where for each cell, just like I had mentioned, 32 by 32 by 256, that's my feature dimension. For each of this cell, now I will have a 256 dimensional vector. For each of this cell, what did I predict? I predict where is the which box is present, which size box. I show you two boxes. So which of this box is present at this location, and then I also predicted the class for this. Okay, the class will typically be, let's say if I have a k class classification, so k dimensional vector, k plus 4 tells me the 4 is the box coordinates. So k plus 4 tells me which object is present in that box. And then because each location may say duplicate objects because the dog is overlapping with multiple cells, so I do a non-maximal suppression and edit. Because there's only a single stage, so this is what we call the single stage object detectors. Yes, is there any question? Is there any question? No. Okay. So the overall architecture will look like the following. So I will have for each cell. So in the case of the YOLO, this is the name of the architecture. In the case of the YOLO, the grid is of size 7 by 7. So for each of the 7 by 7 cell, I'm going to predict the confidence of the object and its location. Okay, that is one. And I'm going to do it for the two object sizes. So I can have two objects at one cell. So one 5-dimensional vector for the first object, and another 5-dimensional vector for the second object. And then each cell will tell me how many, which object is present, which will be a probability vector in the size of the number of classes. So if I have a k classes, so the k dimensional vector. So if I imagine that I have 20 classes here, so we are talking about 7 cross 7, that's the grid size. 2 cross 5, that's the confidence and the box coordinates. And plus 20 is the number of classes here. So we are talking about 7 cross 7 cross 30 dimensional tensor. So this is 30 now, which gives me all the object and classes and its location for this grid. So I will have 1470 outputs from here. And from this 1470 outputs, I'm going to do a non-maximal suppression and suppress the duplicate. Whatever comes out, that's my output. Okay, any questions so far? Otherwise, I can move to the other one. Okay, so let's move ahead then. So now we would like to understand. So we understood the object detection problem. We saw how I can use the neural network model. Typically, in this case, the model that I showed you are the CNN models, so convolutional neural networks. So how the CNN models could have been used for the object detection problem. We saw two approaches, a two-stage approach and a one-stage approach. In a two-stage approach, I predict the proposals first, the location, the likely location. And for each of this proposal, I classify what is the class for each of the box. So that is why I call it a two-stage. And the architecture that we saw for the two-stage detector was faster RCNN. Then we saw how I could have done it with a single stage, which is basically, you can look at it in a way that whenever I generate the proposal, I also generate the class for that box at the same time. So in that case, if I look at this problem, I don't have a proposal and a classification, two separate stages. I have only one stage and I directly output the stuff. So what will happen is that this kind of approach will be faster. Typically, what we'll see is that the two-stage detector may often become more accurate. The one single stage detector may be slightly lesser accurate, although there is this constant upgrade that one can do in each of the architecture. So you can see that some two-stage detector are lower accuracy, some one-stage are higher. But then you can have another two-stage architecture which is more accurate than. So typically what we see is that the two-stage detector may come out to be more accurate, but they tend to be slower. The single-stage detector are faster because you don't have to do this classification in the second pass. You can just do a one pass over the network and get all your object in a single way in the single shot. So they tend to be faster, but sometimes they are lesser accurate compared to their two-stage counterpart. Now, given that, let's say the transformers have become, let's say, the state of the art in many of the problems, the NLP problems, and many of the computer vision problems also. So what we are going to see is that how can one use the transform architecture, the attention-based architectures, for the computer vision problem, or in this case, the object detection problem. So I'll start with the general computer vision problems, and then we will see how we can do it for the object detection problem. So now, for the purpose of these slides, I'm going to assume that the students are already familiar with what are the transformer, how they work, and we're just trying to look at in the context of the computer vision. Okay, so that's the assumption. If there is any question, if there's any doubt, or you don't know what the transformer architectures are, let me know and I can describe it a little bit.
Sir, before moving on to this using transformers in computer vision,
Mm-hmm.
I had one doubt in this YOLO. Like, this YOLO is not having this feed forward network. It's like only using this con layers and directly producing these bonding boxes and class labels. Why are we not using this fully connected layers in that YOLO?
See, I'm not sure whether I would like to see it in this particular manner, the not fully connected, etc. So what we are saying is that the output is a tensor. Okay. So for example, whenever I take this 250, see at some point, let's say the output is 32 by 32 by 256. That's my tensor somewhere in between. Now I can use the convolution and generate this 7 by 7 by 30 tensor. Or I could equivalently look at it in a way that I have a single location, which is a 256 dimensional vector, and I'm applying an MLP on top of it. It's just that this MLP happens to be the same for each of the locations. Okay, so this is where we go typically with many neural network architecture also. So when you talk about this inception nets, etc. So the basic idea was that within a single convolutional layer, you can actually have convolutions of different sizes also. So the idea is, let's say the inception net was one way, but there was another architecture which is called network in network. So the each layer can be as complicated as you may wish it to be. So the fact that I have a tensor as an output, so 7 by 7 by 30 tensor, does not mean that I have to necessarily go it as a fully convolutional way. Although fully convolutional is one of the ways, and it's by far the dominant way also, but it's not the only way. I mean, if you insist that, okay, I do not want a convolution and yet want a YOLO kind of a single state detector, one can create it, one can design it that way. So in that case, what will happen is that I will say that that I have this, let's say 32 by 32 by 256 tensor. I take this 256 dimensional vector and I will pass it through an MLP. And this MLP is common for each of them. Now, this is not necessarily a convolutional layer. At best, I can say this as a network in network layer, because each of the operation is not a linear operation. Okay, so in the convolution, each of this operation is a linear operation. Now I'm doing a non-linear operation for each of the pixel. It is true that I am doing the same operation over the whole image, but it's a non-linear operation that I do over each window. So that's not a convolutional layer, yet it gives me the tensor as an output, 7 by 730 tensor as an output, yet it has a smaller parameter because I tie the weights, but it's not CNN, not convolutional layer.
Yeah.
So, yeah, so I'm just saying that this is a network which produces a tensor output which is 7 by 7 by 30. That's all I'm saying. Whether it has to be convolution or whether it can be something else, this is all open to the designer.
Okay. And also the later versions, like maybe in the YOLO first only, they introduced like something called anchor boxes where getting over the occlusions or something. Then what is the tensor output when the anchor boxes are included?
I was asked to complete it in 45 minutes, so I did not go into the details. So anchor is one detail, but I actually could not avoid but to do it. So when I said that I predict two boxes for each location, so these two boxes are actually the anchors. Okay, so what you're referring to as the anchor is these are two anchors. So in the YOLO V1, there used to be two anchors. And then I predict a box with respect to each of these two anchors and then do the stuff. So as you can see here, when I have two anchors, I have a box corresponding to anchor 1, I have a box corresponding to anchor 2, and then my classification. So I can have more than two anchors also, and it's just that this tensor size will keep on, you can keep on adding 5 into that. So each anchor will add 5 more into the tensor size.
Okay, sir. Okay.
Okay, but ultimately, as the Google thought it 10 years earlier than us, so now this is all tensor flow. So what I'm saying is that ultimately my neural network is taking a tensor. So my RGB image is also a tensor of HW by 3, okay, the 3 channels. And I'm converting one tensor, I'm transforming one tensor to another tensor. That's all we are doing. Now, what does this tensor mean? Or what is the operation to transfer or transform one tensor to another tensor is the only thing that we are changing. Of course, there's a lot of science that is going behind it on what is the operation that needs to be done. There's a lot of insight that one needs to get. But if you talk about the basic operation on the GPU, for example, it's just one tensor transformation to the other tensor transformation. Like it used to be the images. I can just take a convolution. I can take different convolutional kernels and different things will happen. But in a DSP, the digital signal processor, there is only one operation I implement, which is convolution. So one changes the kernel and different outputs emerge. So in this case also, ultimately I'm converting one tensor to the other tensor. Between are changing. Okay. Any other question? Yeah, so there is some noise that I'm getting in between. So if the people don't have any question, maybe they would like to mute themselves so that there's no disturbance. Okay. So this is a single stage YOLO, but both faster RCNN as well as YOLO are convolutional neural networks. So there is no attention as of now that we are talking about. So now let's come to the transformer. So I have a few slides where I just want to say how do you use transformer for the images in general. Okay. So this was one of the first paper which talked about transform for the vision. Okay, and when they say that an image is a worth to a 16 by 16 word, why was that? So before this paper, I said a 2021 paper, we were using transformers in the natural language. So there used to be a sentence, there used to be these words, and the transformer architecture will attend to different word and do something. So for example, I could say what is a sentiment. So take these words, these are my tokens now. Take these tokens and predict a class, which is the sentiment class. If I have to generate an answer to it, so I take a sequence of words, then I predict what should be my first word of my answer. And then once I have the first word, I say, okay, this is my question. This is the first word. What should be the second word? But at any point of time, I have been given a sequence of words. Okay. And then my output is something which can happen to be the next word or which can be the class label. So this is how the transformers were used. It was not clear how one uses the transformer on the images for an image problem. So what did he say? He said that this paper said that let's consider the image as a 16 cross 16 words. So where are the 16 cross 16 words? So here are the 16 cross 16 words. So you say I will divide my image into the patches, and each of this patch becomes my token, or just like in a sentence, like a word. So this is word number 1, word number 2, word number 3. It's just that in this case now the words are not 1D sequence. In a sentence they are typically 1D sequence. Now I have a 2D sequence. So in the case of this paper, they divided an image into a 16 cross 16 patches. Okay. So whatever is your image size, have one cell of such a size so that I have my grid of size 16 by 16. Okay, the patch size will keep on changing, but finally the grid that I will get is 16 cross 16. which means what I'm saying is that my image is in some sense a 16 by 16 words, which is basically 256 words. So I'm converting an image to a sequence of 256 words. And now I can just apply the regular transform architecture, because now these are just 256 tokens to me. So their tokens came from the words, my tokens came from a patch. But once you have got the patch, once you have got the tokens, everything becomes the same for each of the person. So you take this 256 token, just arrange them here. Okay. And now for each of the patches, you just do something. Okay. So there are two ways in which one can do it. So one is that I fix the grid size, which is 16 by 16. The other is I fix the patch size. Okay. And let this number of patches become variable. So both are fine approaches. In one case, we say that the each of dimension is fixed, and the other is we say that the length of the dimension is fixed. Typically, in the case of the transformers, the way they are designed, having a fixed embedding size is important. So what you will do is that each of this patch should have a fixed dimension. Okay, so you divide it into a patch which is of the fixed dimension and then work with it. The later on approaches, just like Swin, etc., what they will do is you will take this image, take a particular patch, pass it through a CNN, and then through this CNN you get whatever this 2048 or 1024 dimensional vector, and that 1024 dimensional vector becomes the description of this patch. So in this case, the input patch size does not matter. For each patch, whatever the size is, I get the fixed 1024 dimension, and that's what I can use later on. So there are different ways, but ultimately you divide the image into patches, and then you just stack these patches into a sequence, and this is your, so this is one word, second word, third word, etc., and this is your sentence. And then the way you work with the transformer and the sentences, in the same manner you can work with the transformer and the images also. So what is typically done in the transformer is that you take this patch or whatever the input dimension and linearly project it to a du dimensional vector. So typically we have this Q, K, and V matrices which convert that into these projection vectors. Then because the location of the word is also important in the case of sentences, so we have that the word is the first word or the second word or the last word. So similarly, in the case of images also, I have the location, which is important. So I add some vector into it, which tells me which location this patch is coming from. So I add position embedding into it. And then once I have this embedding vector, then there is some transformer module that I will use, which will give me the output vectors. So typically in a transformer, the number of input token is equal to the number of output tokens. So if I've given this K tokens here, I will get this K tokens here also. Typically for the classification, how it is done in a transformer is that you add a dummy token, which you can set to 0 or which you can learn through your training exercise, but you add a dummy token and that also comes as an output, but you backpropagate the classification loss from this token. So this is how the transformers have been used for the image classification. So divide it into images, then use add the position embedding into it, run it through the transformer module, just like for the NLP, get your K plus 1 token. So the K from the image and plus 1 is my dummy token, and treat this K plus 1th token as the classification token, and then backpropagate and train it, the model for the classification. So if I have to do the image classification, this is how I will do. Okay, so this is a special token that I add for the classification. Ultimately, when I get this final token corresponding to classification, so I can even have one more MLP on top of it, which will classify into the desired number of classes, because the dimension for all these tokens will be fixed across all the tokens. So whatever is the dimension here, I can take some MLP, which can convert this into a vector of desired size, whatever is our main number of classes. Okay, so this is a computer vision model which have no convolution, because you are just using the linear projection here, no convolution here. And then typically in the transformer also, it's all about attention, etc. No convolution there. So this whole architecture has no convolution. And this is what is popularly known as vision transformer. So it's a transformer model for the vision, computer vision, or working with the images. Okay, now once we have the background for how the transformer will be used for the classification, let's see how I can put it for the detection. Okay, so one thing that I have to understand in this case is that the object detection is intrinsically a set prediction task. Okay, so I have to predict a set of objects. So given a particular image, I have to tell, okay, there are 3 objects in it, or there are 4 objects in it, etc. And in the case of the convolution, how I handle this problem is that I said that, okay, let me have the object proposals, and then I classify each object proposal. So I actually predicted a set of proposal. For each of this set, I could have said that, okay, there exists an object, not exists an object, and that's how I did it. In the case of the two-stage detector, is a set of proposals. In the case of single-stage detector, also I have a concept of anchors, just like I was mentioning. So YOLO was predicting with respect to the 2 boxes, whether there exists an object of this size, whether there is an exists an object of larger size. So what we do is the object detection from the transformer. So this model is called the DETR, which is a transformer-based architecture for object detection. So now what you're going to do is you take an image, take a CNN and convert that into a tensor. Okay, so one tensor to another tensor, in between there is a CNN. So let's say now I have got this, let's say 32 by 32 by 256 tensor. So now I have 32 by 32 tokens, and each token is of size 256. Okay, so I have 1024 tokens, each token is of size 256. So this is like my sentence. So I have 1024 words in my sentence, and each word is being represented by a 256 dimensional vector. So it's like a sentence. So which means that I can use the same transformer encoder decoder which is being used in the NLP. I get a certain set of predictions. But the question is now that I will get a fixed set of predictions. So let's say I get 100 predictions. Okay, so remember there's no proposals now. So these are just 100 prediction. And during the training, I have to say that, okay, whatever is my right ground truth. So for example, this is my ground truth. This is my prediction. So I say that, okay, this prediction matches to this ground truth. This prediction matches to this ground truth. For this prediction, there is no ground truth. So I have to train it in this manner, which is what we call the set-based matching loss. So there's an algorithm for it called the Hungarian algorithm, which does this. And I train my model using that. At the test time, I take all these 100 outputs and I say whichever has got the lowest prediction. So I will do some thresholding. And based upon this thresholding, I will just find out which objects are there. Okay, so there is no proposal and the classification. So remember, when I had the proposal and the classification, each proposal was being independently classified. Okay, so which means that when I'm saying that, okay, location number this, dog or not dog, even if I just move the 1 pixel, the other inference does not really know what I did in the previous case. So it may independently predict whether there is a dog or not dog. And that is why I was required to do this NMS, this non-maximal suppression at the end. Whereas in the case of transformers, typically we go with the query kind of a model. So there is a queries and these queries interact with each other, which means that the 2 proposals actually get to interact with each other. And that is why I don't really have to do an NMS, non-maximal suppression, in the case of the transformer. So I simply do a threshold-based detection, and I say that, okay, whatever is beyond this, above this threshold should be predicted. So this is the detailed architecture. So I'll get this image. So typically we have this encoder architecture, which will convert this into a feature map. In the decoder, I will have got some set of fixed object queries. So you can treat them as like an object proposal. So I have, let's say, 100 object proposals. So I take this encoder features, have this 100 object proposals, and then I just pass it through each layer of the decoder. And ultimately, I will get 100 class and bounding box pairs. And then I simply threshold, because these 100 queries are interacting with each other in the self-attention blocks. They are interacting with each other. So if one query says dog and the other query also says dog and the location is same, this decoder should be able to delete one of them by itself. Reduce the confidence of one of the thing by itself. So the idea is that I do not require non-maximal suppression at the end of the detection pipeline. Okay, so I'm not going to a detail of what exactly is done inside, because you can just see this as a black box, which is a transformer module. I pass in the object queries. On the left side for the encoder, I pass it the image features, and the image features get encoded and then interact with the queries, and I finally get the number of boxes, which is equal to the number of object queries in the input. Okay, so this is how the transformers can be used for the object detection. Yeah, I think this is all from me. This is the detail of the decoder architecture if anyone is interested and any questions. So I hope I am broadly on time. So 50 minutes. Yeah, thank you.
Uh, Thank you very much, Chetan sir, for your wonderful talk.
Sir,
Yeah,
can I
so,
have one question to Chetan, sir?
Yeah, sure.
Yes, sir. Sir, if we talk about transformers, they are computationally heavy. So we just apply one of the technique, that is a distillation to transformers. Like we have in classification task, we have transformers. We just apply the knowledge distillation and we are distilling the response-based knowledge. So what about the object detection? When we have a transformer and object detection, what should we distill?
See, first of all, I mean, the transformers are heavy. I think in general, let's not put this statement because we can do many things in a transformer to make it faster also, or let's say the less memory thing also.
Sir,
So it's not
if I'm applying knowledge distillation, what should I consider there? What should I distill?
knowledge distillation typically works from the output level. So I will
Yes, sir.
get one. So for the purpose of knowledge distillation, whether I use the transformer inside or whether I use the CNN inside is all transparent. The knowledge distillation does not need to know what is inside that. It just says that there is a parent, let's say the teacher model, there's a teacher model and there's a student model. So there is some, let's say, the feature vector which you have learned in that teacher, which you want to transfer to the student. So in your case, I mean, what I understood the problem is you can say that, okay, the transformers are heavy. So I will have a transformer model which will act as a teacher. I will learn a good representation from it. And then my student model will be a lightweight CNN. And I will train the student model through knowledge distillation. So that can happen. So because what you have to do is that you have to take a feature representation on feature. You have to ask the student that you have to match this representation modulo the temperature thing. And then the student will start following that representation using CNN or whatever architecture that you wish to do. So for the knowledge
Okay,
distillation, it
sir.
doesn't really matter that, I mean, both the teacher or student have the same architecture or not.
Yes, yes, so that's a, we can go for the cross architecture. But my question is, what should we distill? We should distill the features, that alignment and all that is another thing. But these features should we distill
Maybe
from?
the knowledge distillation at the feature level, yeah, right. That
Oh,
should.
okay, 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 fine. Thank you, sir.
so there is a one more question in the chat box, sir. So could I read it, sir?
Yeah, sure.
So could you discuss about how we can have multi-dimensional positional embedding like conventional position encoding or 1D?
Uh, See, the positional embeddings are 1D, which is fine. See, all you want to do is that for each position, there should be a unique vector that you can assign. Now, on what basis you assign a unique vector is up to you. I mean, typically we have this cosine and sine kind of stuff where it's easy to do it for the 1D. So you can arrange your patches into 2D and then do that. But you can have a 2D cosine and find your value with that and assign a unique embedding to that. That I don't think that the transformer or anything is really forbidding this kind of stuff. So if you want that, that's also fine. I mean, it's like you have to see typically there are many things which are going on, and one school of thought say that this positional embedding is not really helping that much. So that's also one school of thought, that you just don't have any positional embedding. But my own personal view is that it's just an vector which additionally tells you which is the location of the patch. So what's the harm? So okay, so it does not really benefit much in some circumstances. It will benefit in some circumstances, but that's fine. Let's add a positional embedding. 1D, 2D, to me, they are all okay. I mean, there should be some vector which uniquely specify this is the position. That's all.
For audience, is there any other questions?
Sir, I have one doubt, like regarding that object queries in the for the input in the decoder model. Um, like in normal NLP, we will be giving like a start of the sentence, and then the next word gets predicted, and that's feedback coming from the means will be again given to the decoder. But here, these object queries are we giving input, or is there something else going on?
So, see, typically, if you don't know the length of the sequence, then you have to do the start of the sequence and end of the sequence business. If you have the fixed sequence, then that's not required. So typically in the image, we're talking about the, as I said, the some fixed grid, 16 by 16 grid or something. So if it's a fixed grid, then no end of sequence required really. But if you start designing it in a manner that the number of patches are not fixed, so for example, you want to work with an images of different size, then the number of patches will not be fixed. And so in that case, your architecture should be able to say, okay, it can sometimes get 1,000 tokens and sometimes it will get 800 tokens, and it should be able to work with that. But otherwise, typically start and end of the sequence are required in the generative models. The model has to sort of give a feedback that it's now end of the output. So that's where it's needed.
Here, these object queries, how they are initialized? Like, are there learnable parameters or not?
So yeah, so the object queries have the content and the learnable parameters both. So typically you start with some random vectors or zero vectors, and then you train it over the training sequence. So when you have this multiple epochs of the training, so these embedding vector gets updated with the backpropagation gradient.
Okay, sir. Thank you.
So any other questions? I think there is no more questions, sir. So once again, thank you very much, Professor Chetan, sir, for your insightful talk. So I hope that I would get an opportunity to invite you in such kind of workshops. So thank you very much, sir.
Okay, thank you.